Okay, thank you, Juan. I'd like to thank Juan and Mike Thompson for inviting Leistritz up to speak. I'm going to talk about the technology, but it's my understanding also maybe about some career development, some things about some history, and how many people out there are running twin screw extruders? How many people single screw? How many people know what an extruder is? Okay, you're ahead of me when I went for my initial interview. So I'm going to talk about the evolution of twin screw extruders, where they're at, where they came from. And what's kind of interesting is that, virtually every polymer or plastic part that you encounter, whether it's a fiber, an injection molded part, a foam, at some point the raw material that is making that part has been through a continuous mixer and probably a twin screw extruder. Probably 95% of the plastics you encounter every day have been through a twin screw extruder. So what you're really doing, so it's a technology that everybody uses every day, but they're unaware of the significance. None of you, I don't think, are old enough to, plastics obviously gets some bad press, and some of it well deserved. But I can remember back when I was a kid, we had glass shampoo bottles in the bathroom. So I don't know, can I get a show of hands? Who wants to substitute their plastic shampoo bottle for a glass one? No? Okay, so just checking. Brief word about Leistritz. We're a 2,000 employee worldwide organization. We were founded in 1905 in Nuremberg, Germany. We are in a number of high technology areas. Extruders comprise about 30% of the worldwide sale. We invented the counter-rotating intermeshing twin screw extruder in the 1930s. Others make the same claim. We think we're telling the truth. We manufacture co-rotating intermeshing twin screw extruders from 12 to 260 millimeter, and that equates the 12 millimeter could maybe do a 100-gram batch, and the 260 could probably run 20 to 30,000 kgs an hour. There's extruders out there that can run in excess of 50,000 kgs an hour. So this is a very prevalent technology in the world. We were established in 1976 in North America. That's where my responsibilities lie. We got a fully equipped process laboratory. We do 80 to 100 trials a year, which exposes us to cutting-edge technologies, and I'm going to show you some of those today. And again, in the parts that we see and use every day. This is a slide I got from one of my mentors, a guy named Dr. David Todd. I'm sure Mike knows him. You know Dave, right? He wrote the definitive textbook on compounding. And we're going to talk about suggestions that I have in your career. Whatever career you go into, I suggest you take out a textbook or two and treat it like a course and go through and study it and immerse yourself in the technology, because the more familiar you get, the better you're going to be at it and the more confident you're going to be. But basically, an extruder at the end of the day is a drive, a screw, a heater, and this is the rotating screw conveys and mixes, and I believe the first patent relating to extrusion goes back to 1871. It related to a wire coating process. What do twin screw extruders do? They're continuous mixers. So we take raw materials, pellets, powders, liquids, and fibers. They get melted and mixed in the extruder. Hopefully we've got a homogeneous mass coming out. When it comes out, we're going to size and cool it in water and air on rolls. Then we're going to make pellets that go into a molding machine or a single screw extruder. Or we're also going to talk about going directly to the final product, film, sheet, fiber, profile. 99% of co-rotating intermeshing twin screw extruders are used for compounding, devolatilization, and reactive extrusion. That's what this device is. It's a mixer and a devolatilizer. 90% make pellets, but 10% make something else. And we're going to talk about the similarities and the differences of when you're doing one as compared to the other. This is a shot of a typical system. You've got feeders, you've got the extruder, multiple places to introduce the ingredients, screen changer, and pelletizer. Here is the modern-day twin screw extruder. You've got the motor, the gearbox, the process section. We're going to meter the materials in here, and it's a continuous mixer. We're going to melt and mix and remove gases and vents. And we can also introduce materials downstream in the process, sequentially introduce them, manage the heat and shear history that the individual raw materials are exposed to. The screws and barrels are modular. My former boss, Bill Thiel, used to refer to them as Legos for adults. So what you do is you stack up the screws, stack up the barrels, you match the geometries to the different unit operations that are being performed in the machine. And this modularity of design is very powerful in that you can make the machine shorter, longer, change the shear intensity, make it more passive, and you can really tailor the design to make a specific high-tech product. They're rated for operation up to 400 degrees C as standard. A variety of metallurgies are available, tool steels, powdered metallurgies, nickel-based alloys. So again, can do a wide variety of applications. There's very, very few plastics that aren't processed on this technology. And we talk about the machine being a continuous mixer. So here we've got the screw. Material gets fed in here, it's conveyed forward. And what we're going to do is we're going to take the different raw materials, we're going to distributively mix them, and we're going to dispersively mix them. So if this is what's going into the machine, we're hoping that this homogeneous mass is coming out of the machine. And we're going to select these different screws based on the polymer. So if you're running polyethylene, the screw design is going to be different than if you're running flexible PVC, which is going to be different than if you're running a thermoplastic starch, which is different than if you're going to be running a peak high temperature material or a fluoropolymer. So again, we're going to modify the process section configuration based on the formulation. And this is just a shot, an end view of the co-rotating twin screw extruder. If you look in the intermesh region, we've got opposing surface velocities. So the material is wiped from one screw to the other. And this self-wiping feature in combination with a modular design allows you in a very calculated and iterative way to match screw and barrel geometries to the various unit operations that you're performing in the machine, which generally include feeding, solids conveyance, melt and mix, more mixing, sealing, venting, pumping. So everybody says, oh, what's sealing? Sealing means we're going to have a melt seal here because we're going to pull a vacuum. And so you got to have a melt seal to pull a vacuum. Anywhere we've got flighted elements, the forwarding efficiency of these elements is higher than the feed rate, which allows us to do things like feed material in downstream, put a hole in the barrel to remove volatiles. So this controlled pressure environment is a very important design feature or capability of this device. And this is a shot once the stuff has already been mixed. This is a color master batch line going through water, spaghetti, gets pelletized and then sized. This is called a classifier to remove over and unders. So all the color, it's an industry unto itself. There's probably I don't know, 1,000 extruders out in North America that are making color master batch. And what the molder does is he takes 5% of this master batch, whether white, yellow, blue, and then puts it in with the resin, and then turns his part from clear plastic into a blue part. So again, very typical application for a twin screw extruder. And there's 1,000 or 10,000 different applications like that. That again, we're putting in we're continuously mixing the formulation. This is a shot of a underwater pelletizing system. So we're going to be cutting in a submerged environment. The molten materials pumped through a die, it's cut, you get a very spherical pellet. This is how high volume polyolefin lines run. These systems like this can run up to, like I said, 50,000 kgs an hour. And this is the material that, among other things, makes your milk jug or oil can material. So high volume, the higher the volume, the more automated the line. Here's the silos, reactors, mezzanine. This extruder is putting out 10, 20, 30,000 kgs an hour. It's just a small component in this line. Some of the biggest lines in the world are out at Nova Chemical in Western Canada that would look like this. I started out in the single screw business. We're exclusively twin screws, but there's probably 10 times as many single screws out there. These are making film, sheet, fiber. The single screw extruder is an excellent pump. It can build high pressure. It's flood fed. The screw RPM results in drag flow that drags the material forward. It's melted, goes into the metering section. Here we've got a mixing screw that helps mix. And a lot of times I hear people say, oh, the twin screw extruder is a better mixer than the single screw. And I have to disagree with them. Without stating what the application is, you really can't say what's a better device for the job. I mean, there's thousands and thousands of single screw extruders out there that are used for mixing, but kind of just think of it as, you can get to out of 100 products, maybe you can do 20 or 30 or 40 on a single screw, but then when you get to a certain mass transfer requirement or devolatilizing requirement, the single screw kind of runs out of mixing capability, and then you're compelled to go to a more intensive twin screw extruder. Because it's a flood-fed device and higher pressure, this is a much better pump than the star-fed twin screw extruder. So it really depends on the application, depends on the formulation, what you're trying to do. And all of you, when you get out into the industry and you're trying to make something, just keep in mind that every machine that's been out there in a long-term way has technical merit, and kind of try to get inside it and understand what makes that device better for that particular application or not. Actually, Mike comes from a single screw background too. How many years?
4 years.
4 years. I got 6 years. Early years, this is how some of the early extruders looked like. Most of the twin screws came out of Germany and Italy. What's kind of interesting to me is back in these days, you could get a twin screw extruder, you could get a 4-screw extruder, you could get a 10-screw extruder. So there was a lot of experimentation. And a lot of, when I talk about commercial acceptance, part of that is complexity and long-term maintenance. So what happened is over the next 20, 30 years, a lot of these more complex, more intricate machines didn't hold up in production as well, so they kind of gave way to the twin screw, both co-rotating and counter-rotating, because of their simplicity, utility, and long-term, not as much, nearly as much maintenance required. This is a shot of a 900 millimeter twin screw extruder. This was a custom one-of built for the Department of Defense. Juan, you were there yesterday, so don't cheat on this. And anybody have any idea what this was used for? Guess? Any guess? Department of Defense. Munitions. So the active, the gunpowder or whatever it is held together with a polymer, and this is made the stuff that goes into bombs. And this device was installed in a production environment in a bunker in Nevada. So again, continuous mixer, and there's a whole bunch of different applications like this. Just here is kind of a evolution of the twin screw extruders since the 1950s. The weak link has always kind of been the torque that can be transmitted through the shaft. So if we go back to the 1950s, it was a simple keyweight shaft, a 1.2 OD to ID ratio, and free volume. Free volume is denoted in cc per diameter of the machine. So it's always a trade-off between torque and volume, but this was basically the usable torque back in the 1950s. So then in the 1960s, it went to a hexagonal shaft and a 1.4 OD to ID ratio. And you can intuitively feel that the torque transmitted from this shaft is higher than that shaft. Then in the 1990s, our esteemed competitors at Werner and Fleiter came out with a spline shaft and transmitted more torque than the hex shaft, able to go from 1.4 to 1.55, increase the volume, increase the torque. And then around 1905, there was a development for an asymmetrical spline shaft that isolated the tangential force vector and allowed us to go from 1.55 to 1.66. So again, higher torque, higher volume, and you can tell that in the machinery business, there's usually like a step every, I don't know, 20 years or so. So it's not like we're constantly evolving. We're just tweaking it, we're improving it, and it's a steady incline, and the same analogy that I just went through for the shafts, torque and volume, we could also make for the cooling of the barrels, the temperature control, the heat transfer. So again, we're always trying to get stronger, faster, higher volume, higher rate, just like everyone else. I mentioned before about how the market's going to support machines that have technical merit. These are the three that kind of twin screws that have survived. The co-rotating and counter-rotating intermeshing. The co-rotating probably has 90% market share for continuous compounding. The counter-rotating intermeshing probably has 90% market share for rigid PVC, which is a low-speed, late fusion process. Down here, we've got a tangential counter-rotating, non-intermeshing. This is kind of specialty machine used for reactive extrusion and devolatilization, mainly because of the lack of intermesh geometry and clearances allows the machine to go very long L over Ds, 100 to 20 to 1 L over D, which can be particularly beneficial for those processes. So again, in my profession or my business, I can't tell you how many times I've heard people say, co-rotating is better than counter, counter is better than co, my car is better than your car. if somebody says that without discussing the application, it's really a disservice to you, and that person is probably speaking in forked tongue. So it should always be I have no problem with people saying our technology is best for this application because of this, and this is the study that proves it. You know, then it's a very fair statement. And one of the, we've always gotten, there's only a handful of competitors in this market. Probably 3 of us probably have 90% of the market share, and we've always kind of had an unspoken, or I don't want to say unspoken, a spoken respect, but an understanding that, at least I do, anything that I say in a environment can be repeated to our competitors, because I'm never going to say anything that I believe to be untrue or not completely accurate. And on the whole, and you know, I've been doing this now 40 years, that's, at least in our business, because it's pretty focused and we all know each other, and I think just in general that's human nature. We haven't had any problems, and I think if we all act like that, in the long run, it's better for the industry, for the customers, and for all of us individually at the end of the day. So I don't know why I went off on that tangent. Background. I was born in New Jersey. I went to Caldwell High School. I focused primarily on football and wrestling. I went to Gettysburg College, which is a small liberal arts college in Pennsylvania. I'm a business degree. When I was at Gettysburg, I was, and the operative word is forced to take a variety of courses: foreign language for 3 years, religion. I had to take, not had to, but I had to take science, so I took physics for 3 years. And so I learned a lot, or I learned some about a lot, and always kind of felt inclined that way. I got out of college, I didn't know what I was going to do. I sent out about a bunch of resumes. I got a job at Wells Fargo Guard Investigative Services, and I went down there as I was in training, and the guy that was the head of division headquarters in Prudential Division headquarters in Newark quit. So 30 days out of college, all of a sudden I was in charge of 3 buildings, security, and coordinating and integrating security between Wells Fargo, Prudential, and the Newark Police. It was a great experience. I had a great, my immediate boss down there was former police commissioner in Newark. I learned a lot about people. I learned a lot about managing stressful circumstances, and I learned I wanted to get the heck out of there. I didn't want to be getting called in at 3 in the morning with dead firemen on the floor. So I had interviewed the year before at a company called CHEMENG Extruders, and I went in for an interview, it turns out that I had a lawn cutting degree, and I got interviewed by Jack Killian, and I got referred in there. I take it back from my high school football coach's wife. I went in there, and I asked him if I had a lawn cutting business, and I'd cut a woman named Lori Killian, Mrs. Killian's lawn for 5 years. I asked Jack if he knew Mrs. Killian on Orchard Place in Essex Fells. He said, yes, that's my mother. So I got a job. I said, I'll use her as a job reference. So the moral of that story is I got a job that I was completely unqualified for, selling spare parts for Killian Extruders. And it was a great, best thing that ever happened to me, because what happened is, because I got in selling spare parts, my job was to work with customers that were having problems and issues, and getting replacement heaters it afforded me the opportunity to kind of learn the machine from the from the bottom up. And you know, we were into a lot of primarily laboratory machinery for blown film, sheet, fiber, pelletizing. So I learned a little bit about a lot about a little bit. I don't know which way it goes. And you know, it's just again a great learning experience, great mentor in Jack, and Jack eventually, who passed away, by the way, just last year, sold the company in 1990, and there were some changes that kind of made me inclined to at least be open to other opportunities. I've been working with Polymer Processing Institute down at Stevens Institute, again, a very good mentor, excellent mentor, Dr. Joe Biesenberger. He was the #1 guy in the world at that point on devolatilization. You know Joe, right? And he got me an interview at Leistritz, and I kind of said, well, okay, I've been doing single screw for 6 years. Next step is twin screw. And so I got another job that I was completely unqualified for, so I went to Leistritz Extrusion in 1990, and I'm still there. Just a couple things about football and wrestling. Wrestling is body engineering. So if you're watching a wrestling match, it's torque, and there's a lot of very subtle things in that. Don't underestimate that. And then football, we had a pretty good team, and there's no good football team without teamwork. So everybody you don't have to like each other, but you need to work together. And you can't work against each other, and you can't undercut, because then you don't win the game. Put this up. This is, you know, we're going to talk a little bit more about the evolution. This is a machine from the 1970s. It's still running. So these machines will last 50 plus years. This is doing color master batch. The owner of this company was Bruce Springsteen's sound man in high school. And he also was one of the leading experts in computers back in the 70s, and he knew Bill Gates before he was Bill Gates. Back then in the 70s, they would have the national conferences, and there would only be 200 people there, and it would be Steve Jobs and Bill Gates and Ken Kirchner, one of these guys. So again, this is a color machine. Here, this is the dye, so it's mixing yellow pigment, and this is actually for a FDA compliant for packaging for cosmetics. So it's cool, in this case, in water. We've got the Leistritz proprietary strand guide system, the upside down brooms, the 4x4s, the duct tape. Come on, you're supposed to laugh, that's funny. If you're an engineer, you got to have your duct tape. And again, the classifier. So again, very typical. And I show this up. You know, this wasn't the cleanest facility. Maybe it's not. But I can tell you that this guy has run about 15 lines like this for the last 40 years, and he's a multi-millionaire. And the technology used in this is, you know, a very high-tech product. So just be aware of that. Around 2000, or around the mid to late 90s, when I went to work at Leistritz, it wasn't 90% making pellets; it was 99% making pellets. And one of a guy, Bert Elliott, our engineering manager, came over with me in '92, and we said, "Oh, why are we making pellets to make sheet? Why don't we just put a gear pump on the end and go directly from the raw material to the final product, you know, whether it be filament, fiber." And the boss from Germany was over, and we made that proposal, and he gave me about a half an hour lecture on why it wasn't viable, why it wasn't possible, why it was a bad idea. And he was a brilliant engineer, and he'd done an unbelievable amount of design work that for the extruder, so I didn't really understand much of what he was telling me. It was over my head. So I said, he went back to Germany, and I talked to Bill. I said, Bill Thiel was my boss who'd hired me. I said, Bill, can't we put a gear pump on the end and a sheet die and make a sheet? And he says, we put a man on the moon, we can do that. So we installed a small gear pump and sheet line in our lab, and there's a lot of reasons to go directly from the raw material to the final product. Today we know them all. Back then we didn't really know them. You're going to get less gels. You can put in higher reclaim. You can feed liquids. You can process at a lower melt temperature. You can eliminate the conversion costs. You know, in a 3,000 kgs an hour, it can be substantial. Back then, we didn't really knew it, but we intuitively felt that it was the thing to do. So once we'd installed this capability in our lab, we got virtually, it was the first one in the world that had put that. And you know, that sounds impressive now, but back then it was, you know, okay, we're just putting in a device and see how it works. And today that's now evolved into, you know, so we got all the trials in the industry that people had thought of to do that. We got exposed to all the new processes, and we got, now it's 40% of our worldwide business, and we probably have 80% of the installed base in North America for this technology. So I guess the moral of the story is, test, don't guess, try it, and don't be afraid to take a little risk now and then. And this is actually a shot from one of the first systems out there that was doing a sheet that got thermoformed into a microwavable tray. This was 60% calcium. This product actually made the annual cover of the annual report for Pactiv, and they had determined that the compounders were making more off their product than they were making off their product. So when this went in, they embraced this technology, installed it all over the country, and the engineers all got big promotions. This is the gear pump. Today, it's the same technology you would use for 3D filament. You know, 3D filaments are produced on twin screw extruders, or at least the compounds are. And particularly in an R&D environment, we can adjust the formulation online, and this is obviously a big market. And talk about future applications down at University of Texas in their lab. They're going directly from the twin screw directly into the 3D printer, so not even making filament, melt feeding the 3D printer. Some different applications. This is a biax film line. A company called Bruckner supplies these. They're 140 millimeter class, run at 3,000 kgs an hour. The lithium battery separator film was actually developed in our process laboratory jointly with Bruckner. Very high-tech, so it comes out and it stretches it and stretches it, and that's what gives it the process. Here, there's a trend towards blown film, biaxially oriented blown film for food packaging. And this is just the little lab unit. So this is one of the units in our lab. Can do a 14-inch wide roll stack, or it's fully production rated. We, you know, things like conductive carbon black sheet for resettable fuses. But again, you know, as the machinery company, when we put this capability in our process laboratory, we don't necessarily envision what it's going to be used for, but without exception, there's a lot of smart people out there, and they're going to recognize the tool if they understand it, and then they come in, and that's how products and processes get developed. This is a shot right now. Everybody's big into recycling. This is running a recycled PET. This is a devolatilization process so that we eliminate the drying of the PET so we can pull off the moisture in the extruder. It's a co-extruded process. This is a 110 and a 160. I'm going to guess this line is running at about 3,000 kgs an hour. That's the sheet die. And the J stack, so it goes up and around. And here, that's a close-up of the die going into the nip. So that's how this, the clear packaging PET is made. What kind of interests to me is like, those little ketchup things at containers at McDonald's where you can put an ounce or two in? Those lines run at 2,000 kgs an hour, making these little plastic cups, and that's a lot. I don't know, that means a lot of people, a lot of ketchup. Foam parts by supercritical injection. So again, what we're going to do, back in the 70s, it was master batch and compounding, but now when we have a device and we're going to start thinking about it not as a color compounder or a compounder, but as a continuous mixer. And so maybe we can do things, people approach us where instead of mixing in fillers, we mix in supercritical fluid, pentane CO2, and a process that was developed in our lab was the synthetic wine cork. So again, we're mixing, it's environmentally, actually they're using some bio-based polymers now, but what I didn't realize is one of the reasons this was, that this actually saves on the price of a bottle of wine $1. And it's not because the price of the cork is less, it's about the same, but the natural cork, there's a 5 to 10% failure rate. And when it fails after packaging, you got to basically throw the whole box out because it's not really viable to repackage it. So this is a shot of the supercritical injection. You can see the injection ports here. And this was developed, we actually did a lot of joint research, preliminary work with the National Research Council of Canada and their Foam Tech Consortium up in Boucherville. And then down the road, so we developed SCO2 for injection for foaming, but then we find other applications for it too. Not that we never thought about it, but they found us. It can be used as a stripping agent to assist in removal of volatiles. It can be used as a fugitive plasticizer, particularly for in the pharmaceutical industry where the polymers require some type of plasticizing effect. We're going to match the screw and barrel geometries. We're going to inject the supercritical fluids here. We're going to have a dynamic seal to keep it from blowing back, low energy input pumping elements, minimize the viscous heating, and because you're injecting at high pressure, there's some modifications to the barrel flanges. So again, taking existing technology and tweaking it. And this is actually a video from the History Channel, how it's made, Nomacork. So here's the polymer going in. There's the injection port for the CO2. That's a co-extruder, single screw. That's putting a TPE cap on the foam core, and that allows it to go in and out and be printable for to make it appear to be a real wine cork. Laser gauge to ensure the diameter's right. That's closed loop with the belt puller. It's a triple pass cooling tank, so you've got spray nozzles to cool the extrudate. And then this is my favorite part. Don't put your fingers in here. So that's making the wine cork at about 200 kgs an hour. So again, when I started at Leistritz, it was all plastics and compounding, and then pharmaceutical products. What I didn't realize, now I do, the binder for the drug, API, is a water-soluble polymer. There's a finite number that are approved by the FDA. One of them is polyethylene oxide, PVP, like I said, a handful that you can mix the drug, the active, with the binder, and then you grind it and make it into a pill. One of the major advantages, it's called melt extrusion, is if you just take that for a lot of drugs, if you just take the drug and ingest it, or you mix it with a polymer and press it into a pill, most of it passes through your system. Where if you go into a melt extrusion process, it actually dissolves into the polymer and increases the bioavailability. So it's really was a big step forward for the drug industry. And when I started, so around 1992, we were approached. Well, let me go to the next slide. If you're going to get involved with a market like this, get involved, do something. So, I was approached in the early 90s. We'd worked with a guy, Isaac Gabriel Selassie, that was the VP of technology at Park Davis, currently Pfizer. And he was a brilliant guy. And back then, 99% of there were no extruders used in pharmaceutical. He came to a workshop. He was a visionary and understood the capabilities of the twin. He got a lab machine, he developed, and was responsible for the first drug manufactured by melt extrusion. It was called Resulin. It was an oral insulin to get away from having to do injections. So then he approached my boss about putting together, there was no textbooks on the subject, about putting together a book. Bill was, for whatever reason, was not inclined, was too busy, so Isaac was, I guess, desperate. He contacted me, and so I became the co-editor of this book on pharmaceutical extrusion technology. So what this is, we contacted all the major companies, and at this point, almost there was nothing out there. This is around 2002, and we got the first book done in 2004, I think, and the second edition in 2018. And what this did for Leistritz is a number of our engineers contributed chapters, and it forced me to really, as one of the editors, to go through this technology, edit all the chapters, understand what they were talking about, so I guess the moral of this story is, don't be so quick to say no, even if maybe you're not completely qualified. Just doing it, not a lot of people aren't willing to do it, and if you do it and you can see that there's maybe a light at the end of the tunnel, or might be mutually beneficial, it's normally worthwhile. This is an example on the right. This is an example of increasing the bioavailability. This is without extrusion. This is with extrusion. Again, early development in the 90s, a lot of work at UT under Jim McGinnity in the 90s, but still very slow development. First 10 years for Leistritz in this, from 1992 to 2002 or so, we only sold a handful of machines, and it was deemed a complete and total failure. Because we put a lot of effort and design, and then what happened is in 2004 there was something called the Process Analytical Technology Initiative, came out by the FDA, and it was like it was written by an extrusion guy. And what it was is it was not an edict, but a strong encouragement from the FDA to transition from batch to continuous for mixing or processing for all future drugs. So then, after 10 years and everybody kind of saying, "Oh, gee, Charlie, why do you get us into this? It was bad mistake, and we wasted a lot of time, effort, and money." Then all of a sudden, the next 10 years became 50% of our business. And so then after the second 10 years, and they said, "Oh, okay, Charlie, well, maybe, I guess it's okay that we did it." So anyway, just a story. And we've done things, we've developed products specific to this, but we're never, I'm a big believer in don't necessarily reinvent, but tweak when you can. Don't always try to make something twice as efficient. Do it a little bit at a time. And this was a plunger development because we continually got asked to process small batches for the pharmaceutical industry, and we didn't have a device to meter it, so we came up with this patented device, and we've installed, I don't know, 50 of them worldwide, and it's kind of the standard for small batch development in the pharmaceutical industry. This is a system, pelletizing system for a pharmaceutical product, and you've got containment here because you obviously have drugs that can be active. You cool in air, not in water, and then you pelletize. In this case, this one up top here was making micro pellets for capsule filling. I put this one up just because who's heard of OxyContin? Who's used OxyContin? Don't do it. OxyContin was not necessarily bad, was developed and commercialized in our equipment. So we were involved with this right from the outset. This is the production line that's doing it. And I said this yesterday, don't believe everything you see or hear on a 60 Minutes or a documentary. Purdue's at fault. They didn't act in a pure way, but I can tell you that they, just on a quick note, they did around 2008 or 10, they approached the FDA about a tamper-resistant formulation that was declined by the FDA because the dosage form was atypical, and so it's just not as black and white as you think, but it worked. And this is just the feeder, the vent, the die, the conveyor. Again, most pelletizing lines wouldn't use gauging. This one does because it's making parts. And there's the pelletizer and the classifier. Same technology that's used for high volume production and sheet can be used for transdermal applications. This is a system that's used to make lidocaine is made on this technology. So again, it's you can see the payoffs, the die. This is actually a tandem system in that we've got a counter-rotating rubber extruder feeding a co-rotating compounding extruder. Just a close-up of the die. I mean, it's pretty and shiny, but the technology is identical to plastics. I put this one up. This is one of my oldest friends in the industry, Tim Kane, works at Foster Corp, one of the best engineers I ever encountered, UMass Lowell guy, just passed away, so really good guy. Again, for pharmaceutical, this mostly, there's no utility to this shrouding. The main reason they get it that way is because when the FDA inspector comes in, it looks pretty. And 9 times out of 10, If I go back a year later, the shrouding's all off. So this is, we stopped asking, you know, because it's obviously not cheap, it's all stainless steel, highly polished. We stopped asking whether they wanted it or not, because they just want the inspector to sign off on it. Again, foaming's been embraced by pharmaceutical for fast-acting, fast-dissolving dosage forms. The foaming, the supercritical actually increase the bioavailability. This is a shot of a system that's doing a coax EVA or TPU rod. You can see it's going down into the water. This gets cut to length and welded, and this is a contraceptive device, the NuvaRing. So again, taking existing technology, tweaking it, modifying it for pharma, and the challenge oftentimes is to get the system validated. There's the laser gauge, puller, and winder. We like to work with universities just in Canada. We're involved with yourselves here, McMaster, Mike, John Vakopoulos, University of Toronto, Chul Park, Guelph. Do a lot of bioplastics with Professor Mahanti, Waterloo, Kostas Songanakis, Echo Poli. We've done a lot of work with them over the years. Research Council, University of Laval. And we take, although 90% of our business is industrial, we've learned so much and value so much, and it's not can't even quantify what we've taken out of working with people like Mike